straight up looking at that thing for like 2 minutes.
You guys are a weird couple. Just weird.
We have a study hall.
Yeah, no, that'd be awesome.
I would cry.
Your best friend.
I understand that like it's Friday and we're exhausted. We don't want to do anything, but we're going to do some stuff.
Can we just have some time to do our homework at the end?
We can probably work out some time.
Like 20 minutes?
Here's what I'm gonna. I don't know. I'm not gonna put a number on it right now. But here's what I'm also gonna say: is if I do this and you don't use it, you just kind of screw around and like doodle on your tablets or whatever and talk the whole time, I wouldn't do it again.
Okay. I have a paper.
Just saying.
Strictly math.
All right. So last time we spent like, I don't know, it was like 5 or 10 minutes or something at the end after everyone had finished their test, and we were talking about graphing sine and cosine functions. We had spent some time, we described some of the key characteristics of the sine function and defined a little bit of extra vocabulary, specifically amplitude, period, midline, and frequency. I'd like to kind of continue that today, and we're going to start talking about the cosine function. And we're going to talk about those same attributes here. So the parent function for cosine is just y equals cosine. The domain, just like sine, is all real numbers. The range, just like sine, was from -1 to +1. The symmetry here, though, is different. Let's look at the graph of cosine real quick so we can see the symmetry visually. So here's the graph of cosine. In chapter 1 we talked there was 3 kinds of symmetry that we talked about: symmetric across the x, symmetric across the y, and then that 180-degree point rotation about the origin. What type of symmetry do we see here? It's symmetric across the y-axis, right? We have a special name for that. For functions that have that kind of symmetry, we call them even functions. Remember that we said sine was an odd function, so this is something that's different between sine and cosine. We talked about the continuity of sine was everywhere continuous. The same is true for cosine. The amplitude for cosine is 1. The midline is y equals 0. The period is 2 pi. And the frequency is 1 over 2 pi. So, remind me again, what does the amplitude describe on the graph? Yeah, so it's basically like how high the crests or troughs are on our wave. So the top parts are crests and the bottom parts are troughs, I think is the like geological vocabulary to describe like waves on the ocean. And I'll borrow that same vocabulary here. So if we look at this distance from the crest or trough to the midline, that distance would be the amplitude. That distance is 1 here. Hopefully it's easy to kind of see that. What does the midline describing again? Yeah, the midline is the average value for the function. Basically what it means, it's going to divide the function, so we have half of the graph above that line and half of the graph below that line. If we look here visually, it's pretty easy to see that it's like, if we look at the x-axis, which is our midline for this function, that's the line y equals 0, looks like half the graph is above and half of the graph is below. It's kind of easy to see that visually. What does the period describe? Yeah, the length of one full cycle. So I can count a cycle if I go from maximum to maximum. So if I count it along the x-axis, how far is that? In this case, it's going to be 2 pi. Okay? And the frequency is related to like how many cycles you get per unit, but it's not as visually of a useful descriptor as these other ones are, at least in terms of what we're going to be doing with graphing and whatnot. Certainly frequency matters for other things, but for graphing, it's not the biggest or most important part. So let's just take a moment and compare sine and cosine, because they were almost all of these attributes were exactly the same, right? The only thing that differed was the symmetry. So I'm going to graph sine and cosine on the same axis just to take a look at it. And just so it's easy for us to tell it apart, I'm going to move over to this side here. If I press enter, I'm going to graph the sine with a thick line. So if you go over here and press enter, there's several different options that you can cycle through that look at the graphs for, but it'll make it a little bit easier to tell which one we're looking at if I do that. I think on you guys that have the color calculators, you can even pick the color that you want it to graph in, so it's easy to tell the difference between them. So if you were to look at these two graphs visually, how would you describe the relationship between them? Just in words. They look almost the same, right? What's different about them? Kendall? Okay. That's a reasonable thing. So Kendall says, at first, the sine graph is going up and the cosine graph is going down. Sure. What else do we see? Zach? Yeah, so it looks like they're the exact same graph. It's just been shifted left or right, depending on which graph you're looking at, shifting to the other position. And in fact, that's exactly the relationship I'm kind of hunting for here. So if I look on my scale here, each one of these tick marks is pi over 2. So it appears to me that the cosine graph is the same thing as the sine graph. It's just been shifted left, pi over 2 units. So let's write that observation down, because that's quite an important one. So remember, the h is the thing that controls the shifting left or right. If we're going to the left, that h value needs to be negative. That's why we picked negative pi over 2. So that's an important relationship, and we'll come back to that relationship again here later. So time for another definition here. So we call a function a sinusoid. So if you notice here, these two equations that we wrote down look almost identical to the transformation equations that we talked about in Chapter 1. So if you recall from Chapter 1, we had for the function f of x, its transformation we called g of x, we could write as a times f of 1 over c x minus h plus k. So all we're saying here is that our f is basically the sine or cosine function. We're still just talking about a transformation. So if we're talking about a general sinusoid, let's go through that list that we did earlier for sine and cosine, and now describing any sine or cosine graph. So the parent function that we'd be talking about would be either y equals sine or y equals cosine. The domain, I guess we should probably say the resultant function is going to be these a times sine 1 over c x minus h plus k, or this y equals a times cosine 1 over c x minus h plus k. In either case, the domain is going to be all real numbers, because if we perform a transformation to something that's domain is all real numbers, if I shift it left or right, that's not going to change the domain. Or I shift up and down, that doesn't change the domain. If I stretch left or right, doesn't change the domain if it's infinite long in either direction. If I stretch it or shrink it, it's still infinitely long. If I compress things, that's not even going in the right direction for the range. If I do a reflection across either axis, since it's infinitely long, it still doesn't affect anything. So the domain remains unchanged even with these transformations. Now the range would not be the same, because my range was stuck between -1 and +1. If I shift that up or down, that's going to change the range. If I stretch it or compress it, that would affect the range. Everybody agree with that? So the range changes, and it's going to be affected by the a and the k, because those are the ones that affect whether the graph moves up and down or is stretched up and down. And the up and down is the y's, which are what the range is describing. So my range is going to be the interval k minus absolute value of a, comma k plus the absolute value of a. We'll do some examples here in a moment about like how to deal with that. The amplitude is going to be found by the absolute value of a. The midline is just going to be y equals k. The period is 2 pi times the absolute value of c. And the frequency is just the reciprocal of the period, so it's 1 over 2 pi absolute value c. These facts right here are quite important You want to make sure that you put, like something in your notes that make these easy to find, because you'll need to use them rather frequently. So this is some important facts there that you're going to come back to kind of over and over and over again. So let's do some examples now. So let's list domain, range, amplitude, center line, what am I calling it, center line, midline, whatever, same difference, period, frequency, and then describe the transformation. So the first function I'm going to look at is y equals -4 sine of 2x. The first thing that I'm going to want to do in one of these kinds of problems is rewrite this equation so that it looks like that general sinusoid form up above. So now it's easy to see my values for A, C, H, and K by doing that. The only reason I'm rewriting it this way is so that it's easy for me to justify what my values for A, C, H, and K are. You don't necessarily have to do that in the problem if it's easy for you to see what the values are. But for the purpose of the notes, I think it helps for me to show you how I knew that, say, the C was 1/2 rather than 2, or why the H is 0. When I write it in that standard kind of form there, it becomes kind of really easy to see that. So, the domain for all sine or cosine functions is always all real numbers. Not much to do there. The range is the interval from k minus the absolute value of a to k plus the absolute value of a. So in our case, it's going to be 1 minus 4, comma 1 plus 4, or -3, +5. Everybody happy with that? I just plugged in my values for A and K that I listed above to do that. I also asked for the amplitude. I know the amplitude is the absolute value of A, so in our case that's just 4. Asked for the midline. I know the midline is y equals k. So in our case, we have y equals 1. I know the period is going to be 2 pi times the absolute value of c. So in our case, we have 2 times 1/2, or 2 pi times 1/2. So our period is just going to turn into pi. And then my frequency is just 1 over the period. So I have 1 over pi. Everyone okay with how I just used the formulas above to kind of rattle these guys down? Hallie? Sure. That's fine. Just this one is fine. Yep. Okay. So we still have one thing more to do in this problem. I ask you to describe the transformation. So when I say that, I'm talking about writing down the 1, 2, 3, 4, 5, 6. So 1 and 2 are about C, 3 and 4 about A, 5 is about H, and 6 is about K. So the first thing that we need to check is whether C is negative. RC is not negative, so nothing happens. The next thing we need to check is the magnitude of C. Since the absolute value of C is less than 1, we have a horizontal shrink by a factor of 1/2. For 3, we need to check A's. The first thing we'll check is if A is negative. RA is negative, so we have a reflection across the x-axis. Then we need to check the magnitude of A. Since the absolute value of A is greater than 1, we have a vertical stretch. Since our H is 0, we don't have any shifting left or right. And since our K is positive, we're going to go up and then 1 unit. So this is the same kind of transformation that we described from chapter 1, right? The same kind of idea. We're just applying it now specifically to sine and cosine functions. Let's do another. Yes? So let's say we have 2 times sine negative x plus pi. Let's just take a minute, not even probably, and just try on your own to write down the values for A, C, H, and K. That's the first step. If you cannot do that correctly, you're going to get lots of things after that wrong because they all depend on us being able to identify those values of A, C, H, and K effectively. So I'll just give you guys a minute to try to take a look at what's going on there. You can look back at your old other notes. But try to write that down for yourself, and then in just a minute we'll go through it together. Okay? So, if I wanted to try to write it in that standard form, it would look something like this. So my A would be 2, my C would be -1, my H would be positive pi, and my K would be 0. Kindle? So that's the kind of the standard form. So the h is going to be involving this, and the k would be involved with what's out here.
So if there's no like
Correct. Likewise with h. If you don't see an a or a c, though, what would those be? Not zeros. They'd be 1. And the reason is a and c are being multiplied. When we multiply by 1, it does nothing. So if nothing is happening, the a's and c's were 1. When we add or subtract by 0, that does nothing. So when the h and the k are gone, those are zeros, as opposed to the a and c, which are 1s. You're welcome. Anna?
the end of being negative time was if you gave out the 1 and negative 1? Or I don't understand why.
So notice here, if I look at this piece, it requires the leading coefficient of x to be positive 1. So what I did here is I don't have that. I factored off the negative 1, which causes the signs to switch. So the negative x now becomes a positive x, and the positive pi becomes a negative pi.
Okay, and then you find the h just changes to a positive.
Right, so the h is always the opposite sign of what it appears, just like the c is always the reciprocal of what it appears. Okay with that? What's the domain going to be in this case? This is an easy one. Yeah. All sine and cosine functions or domains their domains are all real numbers. What is the range going to be in this situation? Very good. So I will just write -2, +2. Is that okay? How about my amplitude? What's that going to be? Just 2. Good. How about the midline? You have to write y equals 0. It's an equation, so I need to see that y equals part. If you just write 0, I'm going to mark that down. Okay, it's not completely correct. It needs to have the y equals there, just to be clear. How about the period? Two pi times the absolute value of -1, which is just 2 pi. Lexi? Okay. So this is the general form. I'm trying to write that first equation in the general form so it's easy to pick out the values for a, c, h, and k. So that's the resultant function that we just got done talking about earlier. That's what we want it to look like because it's easy to pick out the values for a, c, h, and k. Well, over here the leading coefficient on the x is +1. Over here my leading coefficient is -1. To fix that, I factored the -1 out. And -1 is the same thing as 1 over -1, so it's easy for me to pick out what the c is. Yeah, if you don't need to rewrite it, that's okay. I like to rewrite it for students so it's easy for them to see how I'm picking these numbers out of the equation. It's only done for that purpose in the notes. It's not a requirement in the problem. Although I find that students that do that typically make fewer mistakes than students that don't. And then the last thing we need is the frequency. What's the frequency going to be here? 1 over 2 pi. Just 1 over the period. Okay. Well, I did, right. So 1 times 2 pi is just 2 pi. So we did. we did multiply by c for the period. And now let's do the 1, 2, 3, 4, 5, 6. So the first one is concerning with what variable? The c. Okay. And the first one we care about whether the c is negative. What's the c in our case? -1. So that tells me I have a reflection across which axis? Y-axis. The second thing we need to look at C is what the magnitude of C is. So what's the absolute value of C in our case? +1, right? So that doesn't do anything. The magnitude either has to be bigger than 1 or less than 1 for it to do anything. If it's equal to 1 exactly, it does nothing. But I have to look, which variable do I look at for 3 and 4? A. So the first thing we look at is whether A is negative or positive. In our case, A is positive, so that doesn't do anything. The second thing we have to do is look at the absolute value of A. What's the absolute value of A in our case? Okay. Since that's greater than 1, I have a vertical stretch. The fact that it's bigger than 1 tells me the stretch part. The fact that we're talking about the A's tells me the vertical part. Okay. For 5, which letter do we look at? H. Okay. What's the H in our case? Pi. So because H is greater than 0, it means we're going right pi units. And the last one we look at is K. Since K is 0, that doesn't do anything. What do you think about this? Stop. Just a lot of little formulas, but none of the formulas are terribly complicated, right? All the calculation we're asking you to do is pretty easy. Hannah? I don't really want to talk about the test quite yet, because it's the first day of the chapter. But these are formulas that you should try to memorize. We'll talk later, come test time, exactly what I'm going to require you to know and what I would give you. But they certainly are going to make the homework go better. They'll make the lectures go better if you're not sitting there going, wait, where is this coming from? If you recognize the formulas when I'm using them. So, like, it's a good idea, even if I don't need you to know them for the test, if you can at least, like, know them well enough to makes your homework easier to do and makes the lectures go better. It's really rather helpful. So you're not just, like, struggling to catch up the whole time where you recognize things that we've done before. Okay? But we'll talk before the test, and I'll be very clear about what exactly you have to have memorized for that. So the last topic I want to talk about today is actually graphing. And the tool that I'm going to use to do the graphing is going to be this transformation map that we talked about back in chapter 1. Now, it was easy to kind of have missed this, but this turns into really a pretty important tool for us in terms of making this graphing much easier. This is something that you should memorize. You're going to use it quite a bit, so you'll probably end up memorizing it just out of convenience in doing the homework, but it is something I would expect that you know and can use. So what this is going to allow us to do is if I take any point from my parent function, I can transform it into a point from into my new function by altering the coordinates of the parent function, the x and y, in that way. I'll multiply the x coordinates by c and then add the h. I'll multiply the y coordinates by a and then add the k. And I'm just going to abbreviate transform function as TF here. So the first thing that we're going to need in order to use this is I'm going to need to know what the key points are. What points am I going to take from the parent function to transform? So I'm going to have a different set of points for sine and a different set of points for cosine. And the points that I'm going to use are going to be values that come from the unit circle. So if I pull out my unit circle, this is not the field I wanted it to be in. This is where I want it. Computer is so slow. This is absurd to open a PDF. So if I'm looking at the unit circle, remind me again which coordinate represents my value for sine, x or y? The y coordinate. Okay. So the values of sine that I'm going to be interested in is going to be 0, pi over 2, pi, 3 pi over 2, and then 360. Basically, I'm just going to worry about the quadrantal values. We call them quadrantal because these are the places where the sine, the unit circle is on a quadrant. So I'm going to use the points 0, 0, pi over 2, 1, pi, 0, 3 pi over 2, negative 1, and then 2 pi, 0. I'll write those down now. So do you need to memorize these? No, because you're going to be given a unit circle, right? You can always go back and read them off your unit circle if you remember that the points we're using are just the quadrantal points. Now, you'll probably use them enough times that you'll end up memorizing them just out of convenience. But if you ever are uncertain, you can just get them again off of the unit circle, which is rather convenient. I'm going to do the same thing for cosine. I'm not going to show you on the unit circle where those numbers are coming from. Rest assured I'm doing the exact same thing, except I'm reading the x coordinate instead of the y coordinate. So far, so good. Haven't really done much yet, but we're getting ready to put this kind of all these ingredients together into making a nice little stew here. Because we've now gotten everything that we need in order to do some effective graphing. Let's do an example. And let's just take, say, for instance, this function that we just got done looking at. As we established earlier, my values for A, C, H, and K are the following. So I'm not going to redo how I came up with those because I'm using the same function we just got done doing an example with. So what I'm going to do is I'm going to take those and I'm going to use them to create my transformation map. The transformation map I always use is Cx plus H, Ay plus K. So in our case, C is negative 1, so I'd have negative x, and H is pi. A is 2, and then K is 0. Everybody okay with how I filled the values in to that map? And since the function we're talking about is a sine function, I'm going to use the key points from sine, or for sine. So for the point 0, 0, to transform this, I'm going to take 0, my x-coordinate, plug it in for x. And I'll take 0, my y-coordinate, and plug it in for y, and just evaluate. So when I do that, I get the point pi comma 0. Everybody okay with that? I'll do the same thing now for the next point. And take pi over 2, plug it in for x, and then take 1 and plug it in for y. When I do that, I get positive pi over 2, comma 2. And as I keep going, I get 0, 0, negative pi over 2, comma negative 2, and then negative pi, comma 0. So I just went and plugged those key points in to that formula over and over again. So now I'm just going to plot these points on an xy axis. This is going to provide my graph. So on the x-axis, I'm going to have my units go up by half pi's. So half pi, whole pi, negative a half, negative pi. On my x-axis, I'm going to go up by 1s and 2s. So there's 1, 2, negative 1, negative 2. Now I'm just going to plot these 5 points. So I have pi 0, pi over 2, 2, 0, 0, negative pi over 2, negative 2, and then negative pi 0. So if I connect these, I'd have something that looks like this. Everybody feel okay there? But what if I, instead of graphing this from negative pi to positive pi, what if I asked you to continue graphing this from, say, positive, or from negative 2 pi to positive 2 pi? And do I need to generate new points? I would not. Once we know what one period looks like, we know what any subsequent point is going to look like after or before that period. So I'm just going to continue on with my pattern. So the next point after this one at positive pi should be the minimum. It should be down here at negative 2. Right? If I continue on with the pattern. And then from there we should go back to the x-axis. Similarly, if I'm starting at this point, the next point left of that should be up here at the maximum, at positive 2. And after that, I should go back to the y-axis. And so I can extend my graph as much as I want in either direction just by following the same pattern that I established with my transform points from my parent, or from my that I generated earlier from that period. Okay? Let's stop here because you guys said you didn't want to go the whole time.